All right, welcome back. Here we are at High Frontier for All, game number 3, which is Race for Glory. We're racing to the planet Mars. This is part number 3. We are going through a tutorial, which is basically a game that was played by 3 people. And we are recreating their moves to learn this part of the game, which is almost the entire core part of the game. So we ended up on a cliffhanger on the last episode because the ESA wants to go to Mars, and they have themselves a rocket that's sitting in Leo right up there. And we are going to figure out now how much aqua needs to be transferred into fuel tanks so that we can make some burns to go to Mars. So the first thing that we need to do is figure out, number one, how many burns does it take to go to Mars? And we're going to follow this path here, and we're going to see how many it takes. So starting at low Earth orbit, we're going to go to the cycler. That's one burn because it's got a magenta coloring there. We're going to go to the geocentric orbit here. That's another burn. Then we're going to go to the Lagrange point here, which is not a burn. We're going to take it this way towards Mars and make a burn here. And that's the third burn. And then we're going to go here to Mars flyby, which gives us a +1 bonus burn. We're going to use that bonus burn on that magenta right there. And then we're going to go into the low Mars orbit, which is not a burn. We're going to do a hazard roll here for aero braking, and we're going to try to land on the cave site. So we need 3 total burns in order to get there. Now, what we're going to do in order to figure out how many fuel steps and so forth that is, looks like my thrust measurement fell down there. Currently, we have a mass of 5. You can see up there, the Robonaut is a mass of 2. And the refinery is a mass of 3. So that's a total of 5. And we have our dry and our wet masses right here on 5. Because we have not put any fuel in there. So we need to make 3 burns. So remember, the calculation that we need to do is we need to figure out how many steps of fuel that's going to ultimately take in order to get there. So 3 burns times 4, and that's that number right there, 4 aqua per burn. 3 times 4 is 12. So what we do as a quick thing we can do is take a look at these numbers down here. 3, 2, 2, 2, 2, 2. Add them up, and we have to make sure that we're equal to or more than that number. So we need to have 12 or more. So let's count them up. From 5 to 6 is 3. 2 is 5. 7, 9, 11, 13. So we have to be on this one right here, 11, in order to get there. Okay, that's how we calculate it, because 13 is greater than 12, 11 is not greater than 12, and so we have to go to 13 steps, and that will take us to number 11. All right, so what we'll do is we'll put our wet mass on 11 and our dry mass on 5, and now we have to take a look and see if we need to do a weight modifier. And in fact, we do. The transport is -1 net thrust. So 5 minus 1 is 4. So this rocket can do a maximum of 4 burns per turn. We only need 3 to get to Mars, so we're fine there. And we're going to have enough fuel in there in order to be able to burn our way and get onto Mars. Now we need to pay for that, right? So what we do is we follow the red dotted line next to the dry and follow the red dotted line and count how many. 1, 2, 3, 4, 5, 6. All right, so we need to pay 6 aqua. We have in this bank here we have 10. So we have plenty in order to be able to do that. So I'm going to go ahead and I'm going to adjust this camera here. Get it back to normal position, I suppose we'll call it for now. And so we have 10. So we need to pay 1, 2, 3, 4, 5, 6. And that's these steps right here. 1, 2, 3, 4, 5, 6. All right. So we pay 6 aqua back to the bank. And that is basically a conversion from aqua to fuel tanks. So remember, one step is a fuel tank, about 20 tons of mass. All right. So now that we have our fuel tanks there, we are loaded up and we're pretty much ready to go. So we're going to talk about a little bit now about movement. So movement is really kind of pretty simple to understand once you get the basics down, and then we can go then we can really start to move our rocket in a good way. So we did our dry and wet mast. We adjusted it based on the weight. We have a thruster in our rocket stack. It's sitting up there. It's a 5.4, as we saw before. 5 base thrust, 4 steps of fuel per burn. And we calculated our net thrust by subtracting the 1. And then at this point, we can also apply afterburners if we want to. We have an afterburner there. It would cost us 1 aqua in order to get an extra burn, but we don't need it because we only need 3 and we can go 4. We're not using a solar powered thruster. We're actually using a push thruster, which, remember, this faction has a power stat ability. So the power stat ability can actually add an extra boost to the, an extra burn to the movement. During any player's turn, may give +1 thrust to a spacecraft that has push in their thruster triangle. So we can actually even modify that up to 5 if we want to. We really don't need it. But since we have the power stat, we're just going to go ahead and we are going to go to 5 because we're able to push that a little bit more with the power stat ability. All right. The final thrust basically determines how many burns you can take in your turn and also where you can land and where you can lift off. All right. So some basic principles. So when you start a movement, you can head off any direction along the route. Okay. That includes those points where they're intersecting. Like, for example, right here. If you stop here and you came from here, you can go backward. You can go this way. You can go that way, or you can go this way along that route. So that's one thing that you can remember and need to remember. So in order to enter a burn space, in other words, one of those magenta-filled circles, you need to be able to pay the cost in fuel as determined by your thruster's fuel consumption. If you can't, then you have to stop on a space before the burn space. So in other words, if I were, for example, here, and I wanted to make and wanted to keep on moving, say I came from here over to here, and I wanted to keep on moving, but I didn't have enough fuel to continue to burn, I could not go here, but I could go here to this space. You can't see. Hold on. One sec. I could go here to this space because that's not a burn. I couldn't go all the way here, but I could stop here. Okay? So that's how that works. You can't stop anywhere except on lander burns while en route. Okay? So you can stop anywhere except on lander burns. For example, this lander burn right there by the moon, can't stop there. You're already committed to land, so you've got to keep on moving. All right? Since you can't stop on a lander burn, you must be able to move to the next space after the lander burn. If the next space is a site, then you must have the means to land. All right? So in other words, on those sites over there on the moon, they're 9H and 9S. So your craft needs to have a thrust of 9 or greater in order to do that. I believe it's 9 or greater. It might be greater than 9. I'm not exactly sure, so we will see. I think I've said it before, but I forgot if it was greater than or equal to or equal to. I'm not exactly sure, but we'll get to that. We don't need to deal with that right this moment. You can turn for free at any space with an icon, but to turn at a Hohmann requires you to perform 2 burns with your rocket. We've said that multiple times now. If you're at a Hohmann crossing, then you want to go from, say, here to here on the same turn, you have to pay 2 burns to make that turn. Otherwise, you wait a turn, and then you can continue on your motion without making a burn. This is called performing a pivot. And you cannot do U-turns, though. So on the same turn, you can't go, for example, from that Lagrange point here to this intersection and then make a U-turn. Can't do that. If you want to go back, you got to wait a turn and then go back. If you have an activated thruster, you get to coast, which is following a route using a negligible amount of fuel until you need to enter a burn space. So again, if we were at that Lagrange point and we didn't want to stop until we went to a burn, we can go here. We can continue to coast, continue to coast, continue to coast until we get to this spot here and we have to stop because we can't make a burn here and we can't make a burn here and we can't make a pivot because we don't have enough fuel. All right. So the thrust triangle we just looked at, which is 5 thrust base and a fuel consumption of 4. That means a single burn will cost us 4 steps of fuel. It has a pushable, which means that it can get a net thrust, a +1 to its net thrust. Lastly, it has an afterburn, like we said, so it can also get +1 thrust if we want to expend 1 step of, I said aqua before, but it's actually 1 step of fuel. Now, we don't need that, so we're okay for now. So the net thrust of the rocket, starting with 5, it's reduced by 1 because of the weight class modifier. And then we use the faction ability in order to have the beamed power modifier, and which is the power set, and we push the thrust back to 5. Now we have our net thrust of 5, and this is plenty of burns in order to be able to go to Mars. So I want to talk real quick about these burn spaces here, the ones that we see in magenta, the colored ones. And some people might ask, well, Why don't you have to burn at a Hohmann crossing the next time you go? Well, not every space costs a movement point. Pretty much every other game, when you go to a space and you want to move somewhere else, it costs a movement point. But because this game, the map's designed using the delta V maps of the solar system. It's a map of energy, not distance. I know they have it laid out in order to show distance, but delta V is basically the change of velocity that's required to go to places in space. I'll give you an example. The Earth orbits at a speed of 30 kilometers per second, but Mars, since it's farther away from the sun, orbits slower, only at 24 kilometers per second. So the delta V between the Earth and Mars is at least 6 kilometers per second. Now they've got this calculated in the game that each burn is equal to 2.5 kilometers per second of delta V. So if the difference between Earth and Mars is 6, divide that by 2.5, and you come up with 2 point something. I don't know exactly the calculation, but it's over. It's probably what, 2.4 or something like that. So it's more than 2 and less than 3. So you basically have to have 3 burns in order to get there, which is exactly how many it's going to take in order to get there. That is the explanation of why it takes 3 burns to get there, is because the delta V between the two bodies that we're going between, the Earth and Mars, is a difference of 6 kilometers per second. And delta V in this game, 1 burn is 2.5. All right. So hopefully that helps understand this a little bit better. Each time a rocket attempts to move onto a burn space, it expends the number of fuel steps indicated by the fuel consumption number on the thrust triangle, which is 4 in this case. And so we're going to follow the blue line to Mars. So the rocket is sitting in Leo. And we want to move it to a highly elliptical orbit, right? Which is the cycler burn space. So the cycler is well above the Earth, out of low Earth orbit, and it's an elliptical orbit, which means that part of its orbit is closer at its apogee, at its perigee, than it is at its apogee. So apogee is the maximum distance that it goes away from the Earth, and the perigee is the least amount of distance that it goes away from the Earth. So it could orbit at 10,000 kilometers and get as close as 6,000 kilometers, but it never lands on the Earth. It's always in orbit, and it basically goes from 10,000 to 6,000. And as it gets closer to the Earth, it speeds up. And as it gets farther away, it slows down. And then it comes back around and so forth. So that's what the cycler is. It's basically a nice wide orbit around the Earth. And that's what we're going to do. So that costs us 1 fuel step, it costs us 1 burn, which is 4 fuel steps. 1, 2, 3, 4. All right. So that's where we are. We made 1 burn. Now, what we're going to do is we're going to go we're going to talk one more moment about the cycler, okay? The cycler is a transfer orbit that links the low Earth orbit to other orbits of interest, right? We just explained that. The cycler burn space represents several possible orbits, including the geostationary transfer orbit, GTO, that allows a spacecraft to move from LEO to geostationary orbit, GEO. Cyclers are typically highly eccentric and elongated ellipse rather than a circle. The GTO cycler intersects LEO at perigee and GEO at apogee. Okay? So think about that. Here's your elliptical orbit going around and hitting GEO and then coming around and then hitting LEO and then coming around and so forth. So starting at LEO, we're just going around the Earth at about 200 to 300 kilometers high. And then we burn up in order to go out further and then come back around. Okay. So that's one burn. Now let's talk about the fuel strip. When you add fuel to your rocket, you move the wet mass chip along the red line, but when you use fuel to burn, you move the wet mass chip along the black line. Why? That's because of the rocket equation. Neglecting air resistance and relativity, a fixed change in velocity, delta V, which High Frontier models as a burn space, uses up a fixed fraction of the wet mass of the rocket. So if you have a rocket with a wet mass of 200,000 kilograms and your fraction for a burn is 0.1, then you'll use 20,000 kilograms of fuel to enter that burn space. If you have a rocket with a wet mass of 100,000, then you only use 10,000 kilograms of fuel. So fuel tanks are fixed amounts of water. I said 20 tons, but in fact, it's 40,000 kilograms, TONNES. Okay, 40 tons. So it's 40,000 kilograms of water. When you add fuel to your rocket, you do it in fixed amounts of mass. But when you use it, you remove a proportional amount. So in the example here, a single burn for a rocket with a mass of 200,000 kilograms uses half a fuel tank. But a single burn for the 100,000 kilogram rocket only uses 1/4 of a fuel tank. See? So at low mass, the black line is longer than the dashed red line, which just proves the game designer is a genius. And it says he doesn't even know that I wrote this. So that's why you see here that you have these red spots that are less and shorter than the long black lines. All right. So now we're going to move the rocket for another burn. We're going to move it from the cycler through this radiation spot, which is not a magenta, and the radiation spot is actually not used in the Race for Glory version of the game. It will be used in the core game. So we go through that and we make our burn here at GEO, which makes sense because when you are the farthest away from Earth and you want to get even farther away, what you'll do is you'll make a burn at apogee in the direction that you wish to go, and it'll take you even farther away from Earth. At a certain point, you'll be going so fast that Earth's gravity will no longer affect you, and you'll be able to escape the orbit of the Earth, and you'll go out further out and orbit something else. Most of the time, that's going to be the sun because the sun has far greater gravity than the Earth does. So that will basically be represented just like what we're going to see right now. So we're going to make this next burn here at GEO. We made the first burn to get from low Earth orbit up to a little bit higher, and so we can increase our orbit out to the GEO. We did that by going to the cycler. Then we went from the cycler out to GEO, and now at GEO we are making this burn in order to basically escape the Earth's gravity. So what we do is we come around here and crash our rocket. Sorry, not crash it. Go to here to the Lagrange point. Now see, this is the solar Earth Lagrange point. And from here, this is where we can escape the Earth's gravity, and we can go out into other areas of the solar system. So this is our, for example, this is our one. We made 2 burns so far, and we're going out even further. Now we're going to take this blue line out here, and we are going to go from the Lagrange point, which is not magenta. We're going to go out here. We're not going to stop at this Hohmann crossing. We have another burn right here. So that is our 3rd burn. We are going to mark both those burns down here on our fuel strip as being taken. Okay. So this wet mass marker, we made 2 burns. So that's 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. We're right there, right before the dry mass. So we don't have enough fuel to make another burn. Okay. We've already made our 3rd burn. And so we're going to get nice and close over here. Yeah, that's nice. We're going to make our 3rd. We made our 3rd burn back here. And then we're going to go up here. And at this spot right there, that is a Mars flyby spot. Okay. And the Mars flyby spot says +1. So we get 1 free burn. All right. Right here, we're going to go through this spot here. And let me see if that spot there requires us to do anything. So we exited along the blue line. We would have to stop unless we have enough fuel, but we already did that. So we moved our wet mass chit down. And now we don't have any more fuel for the burns, but we can coast provided we don't enter any more burn spaces. As you can see, along that line, the next thing is going to be that burn space. But we did get a +1 for the flyby. So we earned a bonus 1 here. And the flyby is basically exchanging momentum between a rocket and a planet will increase or decrease the relative speed of both. This maneuver, called a flyby, but is also referred to as a gravitational slingshot, or more formally, a gravity assist maneuver. It essentially provides free delta V. Voyager conducted a series of gravity assists to build up the speed necessary to escape the solar system using Jupiter, Saturn, Uranus, and Neptune. So if you remember the Voyager probe, that used the gravity assist from the outer planets in order to build up speed to continue to go towards the other outer planets and ultimately exit the solar system. So we have this, we have a bonus burn here, which is great. And we're going to, it says, by using Mars as a gravitational slingshot, this would be really useful if she was going further, but bonus burns can't be used to enter lander burns. So the flyby space is a Lagrange. So we can choose the direction to exit, and we choose the dotted arrow brake path. Okay? That's what we're going to choose. We're going to choose the dotted arrow brake path. And that is this path right here that we're going along right now, the dotted one. So we're going to choose the dotted arrow brake path. And there's no the reason for that as well is that the ship is a net thrust of 5 and Mars is a size 10. So we can't just land on it using our thrusters and land nice and soft. We actually have to do aerobraking in order to basically land this thing. In other words, we're going to use the atmosphere of Mars to slow us down. So, and that takes us right to the burn space just before LMO, the low Mars orbit. So we have a we have one thing that we have to do in order to get to the low Mars orbit, and that is to pay. We have an option. We can pay for Aqua in order to do a thing called FINAO, FINAO. FINAO is failure is not an option. So we're going to use the 4 Aqua that we have in our bank, and we are going to pay that 4 Aqua in order to move through the spot that we're on right now, go on to the burn spot, and use our bonus burn in order to go into low Mars orbit. Now, from there, this is not a magenta, so we can continue to move, and we are going to move over here in order to get to the caves. This is also an aerobraking movement. So we did an aerobraking before in order to get to low Mars orbit. And now we're doing another aerobraking to actually land on the planet. So the person doesn't have any more Aqua to be able to purchase another failure is not an option. So they're going to have to roll the dice. And believe it or not, this person did roll a 1. And as you can see, 1 is disaster. The spaceship did not aerobrake properly and basically crash landed on Mars, which, as you can imagine, is not good. Not good at all. So the rocket crashed and explodes. All cards from the rocket stack undergo involuntary decommission, forcing her cards back into her hand, the removal of her rocket figure, and the loss of all fuel on board. So they did not reach the destination, unfortunately. So close, all down to the very, very last aerobraking maneuver, paid all that Aqua and got nothing for it, really. That is space. As I've heard, space is hard. So anyway, that is what happened. As I said before, the person lost everything in their rocket stack. In other words, these 2 here go back into their hand. Their hand will be over here, right there. I'll clean up this a little bit. This is these are the patents available for auction. And this is a refinery here. Well, that's really messy. Okay, that's better. All right. We have the crew there. These are the cards that are available for auction. There we go. Okay. And the rocket is lost. So we'll take the rocket off the board, put it back onto their placemat, take the thruster thing off. The chits, the wet mask goes here. Sorry, you can't see that. There we go. The dry mask chit goes over here. And that rocket is gone. No longer available for use. It is gone. Unfortunate. But that's the way cookie crumbles sometimes. So we're returning these things to hand. The XRISM is a remarkable X-ray calorimeter instrument launched by the Japanese Space Agency, JAXA, in 2016. Unfortunately, a glitch in the inertial measurement unit of the Hitomi satellite that was carrying the XRISM to spin and fragment. This sent the X-ray telescope back to the hand. See? XRISM is due to be launched by the JAXA H-2A rocket. It was scheduled to be launched in January 2022. Don't know if it did. I'm not sure. But anyway, that's basically what it represents, is that failure, catastrophe in space. You lost what you had up there, but you still can build it again. All right. So that is there's a lot of different paths that we can go. We showed that the blue route that allows to go to low Mars orbit to be reached within three burns in a single turn, but it does force your rocket to risk an aerobrake hazard to enter the low Mars orbit. The more conservative red LEO to Mars route takes more than one turn if done with only 3 burns, but it also has fewer hazards. The colored pass and the signpost provide you with guidance, but in the end, the decision is yours to make. All right. So that person decided to go really risky and fast, and it did not pay off. Here we are. We're going to the next year. Year number 11. All right. So in year number 11, the taikonauts over here have a couple of things up in low Earth orbit. They have the crew that began there, and they also have a thruster. So what the taikonauts decided to do is they're going to boost their Cat Fusion Z-Pinch torch Robonaut and the CBD molding refinery into Leo. That would be these 2 cards here. Mass 3, Mass 3. That's a total cost of 6. So this stays there. And they actually have exactly 6 in their bank. That's going to cost them all of that in order to boost that up to the low Earth orbit. Of course, NASA has their faction privilege, and they gain 1 for somebody boosting something. So there you go. All right. That was the taikonauts. They boosted it up there. NASA now has a whole bunch of aquas, and NASA is going to do a free market operation and sell the black body pumped laser Robonaut. This one here, because it doesn't need a Robonaut, needs cash. So this one here is gone. And it receives 3 aqua for selling that patent. So we should have 10 aqua up there. Well, we have 3, 6, 9, and 10. All right. So NASA now has 10 Aqua there. The poor ESA, which we thought was well out in front, has spent everything that they had, and they're not in good shape. They don't have any cards to sell. They have to take an income operation just to get one Aqua. Basically starting over. It's very sad. So at the end, the ESA is pretty much starting from scratch due to the mishap. NASA's in pretty good shape with all the components that they need. And they're also getting a bunch of Aquas. And the Taikonauts over here have pretty much like ready to boost everything into Leo and get this rocket underway. So we're going to go to the very last year on this cycle. There we are. And we're going to focus here on the Taikonauts. They need Aqua in order to be able to fuel this rocket. So they're going to go ahead and take an income operation. And they're going to get one Aqua. NASA, who has 11 Aqua, you have 10 here plus one over here, decides now it's time to boost this thruster here with a 5 mass. So they're going to boost this thruster up into low Earth orbit, and it's going to cost them 5. 1, 2, 3, 4, 5. And then they get one back because that's their faction privilege. So now they have all their stuff up into low Earth orbit. And NASA is also going to use a cargo transfer free action. If we remember what that one is, it basically creates a rocket from the stack in Leo, consisting of the thruster and the Robonaut. So, like kind of a smart move by the ESA, they did not bring their crew to die and crash land on Mars. This person saw that and says, well, I'm not going to do that either. I'm going to just bring my thruster and my Robonaut. I'm not going to bring my crew. And I'm going to take myself to Mars. So this person says, all right, great. I made myself my very first rocket. So I'm going to put that thing up in Leo. So there it is. Now we have a white rocket over there in Leo. And the person also did not bring their refinery. As you can see, it's sitting right there in the low Earth orbit, but not assembled into the rocket. They're going to do that, take that later on down the road. Probably because of the mass. Still, it's extra 3 mass. So, it's not the only possible approach, though. Could have waited longer and then sent the refinery along with it by putting more Aqua, converting them into fuel tanks so that there could be more burns available. So, but this is what they chose to do. So we put the white rocket there on the Leo. You can see that way down there on Earth. And the NASA's rockets got to get to the low Mars orbit, and then they can either take the lander burn route down to one of the Mars sites, or they can take the aerobrake path and pay for phenol, or they can take the aerobrake path and risk the hazard roll, as we saw. So let's take a closer look at the red route that this person's going to take. So I'll put this over here. Sorry about the shadow of the camera, but let's see if I can fix that a bit. Yeah, that's better. All right, so they're going to take this red route here, and you can see that it goes all the way up there to Mars. That's a pretty good shot right there. All right, so we have the white rocket sitting on Leo, and in order to get to Mars using that route, it's 3 burns, but it takes 2 turns. So that's the difference between taking the red route and the blue route. The red route is a slower, wider arcing path towards Mars. Takes a little bit slower, but you get there also a little bit slower. And we want to be going slower, remember? Because of the delta V. So what that person had to do when they went on the blue path is they were coming in hot. So they had to do 2 different aerobraking maneuvers, and one of them was, as we know, not a success. So this person saw that and said, I'm going to take a longer way there. So it's the Hohmann just beyond the L2 here, which is this Hohmann right here. They're going to stop here. See, that's the key. You burn once here, you burn twice here, then you come down. You don't burn again until you go all the way up here to this dot right there, which the little logo is there. But you'll see, come up here, Lagrange point, do not burn, and then you burn here. See, that's the 3rd burn. And that's also the Mars flyby. And what that person did is the other person went to low Mars orbit, then went to the aerobraking, and then crashed. This person could do that and then do 2 aerobraking maneuvers to go here, or they could take a longer route and go this way. So there's a few different paths in order to get there. Let's see which one they took. So yep, we wait until the next turn to leave in a new direction at the Hohmann down here. It's a little bit lower. There we go. Down here. And then we'll go back this way. That way we won't have to expend any extra burns and don't have to take as much fuel. If Hohmann's were always the minimum energy route, the map would just be pure spirals. But this ignores the effects of gravity at the embarkation and destination planets. Lower energy routes wind between the Lagrange points, which are unstable gateways to highly perturbative, chaotic trajectories to all other Lagrange points in the solar system. These routes, called the Interplanetary Transport Network, require almost no fuel, but they are glacially slow. Additionally, launch windows are sometimes decades or even centuries apart in order to hit those Lagrange points at the exact point when the planetary bodies are in their proper spot in order to not affect them gravitationally. Signposts always show the minimum number of burns required. They aren't always the fastest route, but they are generally economical. So we can see here that Leo to Mars is 3, and that's an economical way to get there. And it takes 2 turns. So we're going to have to figure out how many fuel we need to take on this journey to Mars for this rocket. And this rocket here has a thrust of 5 and a base thrust of 5 and a burn step of 1, which is really pretty darn good. So let's go down and take a look and calculate how much this is going to need to take. So we'll move this back along here. We know it's 3 burns, so we're going to move this thing back here, and we're going to take a look at their play mat in order to determine exactly what's going on. All right. So first of all, we're going to have our rocket cards. We're going to put these up here for just now to basically calculate what what our mass is and all that stuff. So we have a dry mass of 7, 2 plus 5, right? We know that we have a base thrust of 5 plus we know we have 1 burn, 1 step of fuel per burn. So the base thrust of 5, I'm sorry, the base thrust of 5, the dry mass of 7. And now we're going to have to calculate how much water or aqua that we need to put into this in order to get 3 burns. All right. So we're going to add the intervals, and we go from 7 to 1, 2. We're going to have 3 aquas of fuel that we need to add. So from the dry mass of 7, the intervals are going to be 7. However, this person has decided that they are going to make the pivot at the Hohmann and do that all in one move. So they're going to they're going to need at least a net thrust of 5, and they're going to need to be able to make 5 steps of burns. So we're going to add them up, and we see that between 7 and 8 is 2, between 8 and 9 is 2, and between 9 and 10 is 2. So that's 6. 6 is greater than 5. So the wet mass we're going to put on the space number 10. 2 plus 2 plus 2 is 6. 6 is greater than 5. We follow the red line. That's going to cost us 1, 2, 3 aqua, and we'll be able to get 6 steps of fuel, and that's going to be basically 6 burns. But we only need 5 to get there because we're going to make that pivot. So there we go. Now we're going to take a look and see what the net thrust is. So the net thrust is 5, and the transport is a net thrust of -1. So the thrust is only 4. That is a problem, isn't it? Because now this person can only make 4 burns. And that's not good. They want to be able to make 5. So how do they get to that 5th one? Well, they take a look at their thruster and see, is it a push thruster? No, it's not a push thruster. So they can do no negotiations with the ESA in order to get that power sat privilege in order to be able to push that thruster one more. However, they do have an afterburn. That's this icon right here. So by spending 1 fuel step, they're going to be able to actually raise their thrust by 1. So what they're going to do is they're going to drop the wet mass down 1 fuel step to 9.5, and that's going to bring their thrust back up to 5. So we went from 10 to 9.5, and we went from 4 to 5. So now we've got a net thrust of 5, and we have 5 burn steps available to us, which is basically 5 burns since it's 1 per burn. So this person's going to be able to go to Mars in 1 turn because they used the afterburner. All right. So let's do some movement. Let's do some movement. Now that we're fueled up and ready to go. Oh, sorry, I didn't pay. Yeah, NASA, you got to pay. You got to pay. It was 3 steps. 1, 2, 3. Got to pay the 3 aqua. If you don't pay the 3 aqua, you're going to get in trouble. Now we're going to move. And as I promised last episode, we are going to land on Mars this episode. So we're going to, over here, we're going to go up and burn. For the cycler, we're going to burn to Geo. We're going to go down to the Lagrange point here at L2. We're going to go down to the Hohmann crossing, which is over here. We're going to make the pivot for 2 more burns. We're going to go all the way along the path here to this Lagrange point, which is the Sol Mars Lagrange point. And then we're going to get a little bit closer here. And then we're going to go to the final burn and the 5th to enter the burn space near the LMO. Boom. So we did 1, 2, 1 at the cycler, 1 at Geo, 2 at the crossing, and now the 1 here at the here. Now we're going to go to the low Mars orbit. That is not a burn point, so we're okay there. All right, we made 5 burns. So let's go ahead and instead of continuing there, we're going to go back over here and we're going to pay off those burns here. Okay, so 1, 2, 3, 4, and 5, right on top of the dry mass. So we're out of fuel, but that's okay because we're in low Mars orbit and we're going to be able to continue to get down onto the surface of Mars. So from here, the rocket cannot reach Mars using a lander burn because, okay, here it is. The net thrust is not higher than the sight site of 10. So you need a net thrust higher than the sight in order to be able to take off and land. It can't be equal, because I guess equal means you're not going anywhere. You're sitting on the ground. Or coming down too hard and basically smashing into the planet and breaking up your rocket. So you need something that can overcome the force of that gravity either way, by taking off or by landing nice and soft. So they do not, they only have a net thrust member of 5, so they cannot land directly there. And there's no fuel. So what she planned to do was follow the air brake path down to touch down on the caves. The cool thing about that is here's the aero brake. Remember last time the person rolled the die and they got a 1 and blew up. Well, this time, since they used those extra 2 burns, they didn't have to wait a turn and they didn't have to have the extra air brake. They actually have 4 aqua in order to be able to pay for it. 1, 2, 3, 4. So they're going to pay this 4 aqua right here. And failure is not an option. So guess what? They just landed on Mars. Right there. I promised you that we were going to land on Mars this episode, and we sure enough did, but it was down to the wire. Literally no aqua remaining and no fuel remaining. Perfectly planned, I guess you could say. but NASA did it. NASA is the first one on Mars without a crew, just with a robonaut. So technically, this is what, 1976? I think that was probably the first one that actually like didn't get there and just crash into it, but it was able to send back pictures and so forth. I'm pretty sure that's when it was. So technically, we're in 1976. Anyway, I hope that you enjoyed this part 3 of High Frontier for All, Race for Glory. Again, this is it seems very complicated, but once you understand the mechanics, it's getting easier, I think, for me and hopefully for you to follow as well. So, yeah, anyway, we made it to Mars, and the next episode, we'll see if somebody else can make it to Mars. And we'll also see if they can send some supplies and maybe a refinery over there in order to be able to create some kind of factory. So we'll see what happens next. We'll see if we create an outpost. I don't know. Anyway, stay tuned for the next one, and we'll see you next time.